Hello everyone out there in YouTube and Google Plus land. Here we are for another ATA EB Group seminar, this time in the glorious Building 80 of the RMIT City Campus. It's a change up in venue. We're usually at Swinburne, but we've switched sides today so that we can see how RMIT is faring in their electric vehicle racing team. But first off, let's see if we can just get a little bit of news and events happening. First off, for those that know the Australian Electric Vehicle Association, a very highly respected and reputable association dealing with all things electric, are having their Go Electric Sustainable Transport Festival on Saturday and Sunday, the 25th and 26th of October. I'll just show you their flyer. Are we seeing that good? Okay, so that's at Coburg Town Hall on Urquhart Street. From 10 a.m. to 4 a.m. if you want to go for the festival side of things. And on the Saturday, they have speakers. The speakers will be Stephen Bygrave of Beyond Zero Emissions, Dr. Christopher Jones of the Australian Electric Vehicle Association, Peter MacArthur of Charge Point Australia, Paul Patton, our very own ATA EV Group member on battery technology, Dr. Clint Steele, our brethren there at Swinburne University, and also Bryce Gatton, who we all know is an absolute whiz under the bonnet of all electric vehicles and has converted quite a few vehicles himself, and being a Sparky, he knows what he's doing. Not only that, but also the new issue of the ATA Sanctuary magazine, and there it is out and about now. So rush to newsagents or download or do whatever you need to do, beg, borrow and steal to get yourself a copy. It's well worth the read. And if you do come here to our meetings, which we'd love you to do, you can buy them from us cheap, and we get all the proceeds so that we can keep running our group and bring all things electric to you. Just a little bit of EV news, that Nissan has created Leaf Ute. It isn't going into production, unfortunately, but it is something quite interesting to look at. So if you noodle around on YouTube, I'm sure you'll find that. Also, Renault has introduced the EO Lab. It's a prototype plug-in hybrid that reaches economy figures of 1 litre per 100 kilometres with a 60-kilometre range in electric-only mode. So it's good that Renault are pushing ahead with their forays into the all things electric. Also, fast DC charging in an overhead station mode is being developed in Switzerland. So that's also something to see, and hopefully fast charging of trucks will be, and of buses will be something that they'll be seen in European streets very soon, and hopefully that filters down to us here in Australia. Also, there's talk about a nuclear battery as being a possible technology of the future, using beta voltaics that generates power from radiation. We'll see how that goes. Also, BMW i3 is a hit in the US with sales figures rivaling the Tesla Model S, according to some sources. Also, Golf, VW Golf, well, VW have got a Golf which is a plug-in hybrid with figures of 1.4 litres, with 1.4 litre petrol engine, 100 horsepower electric motor, which is coupled to a 6-speed gearbox, and an 8.8 amp hour battery. The voltage I don't know of yet. It can do 0 to 100 kilometres an hour in 7.6 seconds, and returns figures, economy figures of 1.5 litres to 100 kilometres. So it's still guzzling some petrol, but at least it's a halfway house to sustainability. Also, Foxconn, the maker of the iPhone, is investing $800 million to develop electric cars in China, which is a very good step forward. Not only that, but also in China as well, Vmoto, the electric scooter maker, has bought a Chinese electric vehicle controller manufacturer. So hopefully that means that things will be moving ahead faster on 2 wheels. We also found out that London, which has had hybrid buses for a short time now, is also now installing inductive chargers at bus stops. So as people are getting on, some chargers getting on board the bus as well, and hopefully the diesel motors will be a thing of the past. Some other news. Also, I've just heard recently that El Fomo, a sports racing electric vehicle, competed against some ICE, some internal combustion engine cars in New South Wales recently. Won both its races and set a new lap record. So search that out on the interwebs and see if you can find some more information on that. What else have we got? Also, news out, there's a 2-speed hub motor that is now just coming available out of those tricky people in China. It spins one way for 1 gear and then slips into reverse in order to access a second higher gear to increase the amount of torque and speed that hub motor can deliver. So that's something exciting. It's something I wouldn't mind getting my hands on, having a bit of a try at. Also, Audi in Europe has started selling e-bikes, just a sort of a generic brand, or probably their own Audi brand, but they've started selling those in Europe. So e-bikes are certainly starting to grab a hold in the rest of the world. And is there any other news? I think that's about all the news I have, but just once more, I'd just like to plug the Go Electric Sustainable Transport Festival. Sunday, 26th of October, 10 a.m. to 4 a.m. at the Coburg Town Hall and Burkhart Street there in Coburg. Something worthwhile going to, and run by those lovely people at the AEVA. Now, today, being here in RMIT, we have got Professor Simon Watkins and Jeff Pearson to speak about their forays into the world of electric vehicles and their race car. So I'd just like to invite Simon up to begin his talk, and thank you very much.
Yeah, thank you very much, and welcome to RMIT in RMIT's flashiest building, and I think RMIT's flashiest lecture theatre. So Jeff isn't with us today, but what I was going to do first of all is to give a little background and snapshot of how some of this started. When I mean some of this, I mean Formula SA Electric. And so without further ado, I'm going to talk a little bit about what Formula SA is. And it started about 30 years ago in the States, where the industry decided, the automotive industry decided, that it wanted to get more industry-ready graduates than they currently got out of the more traditional academic universities. And students basically are charged with designing and building a small open-wheel race car. Every year they do that. That's a fairly easy thing to say, but it's an incredibly challenging thing to do, because some of the students haven't really done much practical work when they came here. It's a mixture of our technical college, so our TAFE college, and degree students, so higher ed. and sometimes postgraduate. So it goes right across our seamless university, going from initial sort of apprentice type training right up to maybe PhD students. And our cars are designed mainly in Bandura, but some of them are designed here. So we have two campuses. One is up north of here, about 20 kilometers away in Bandura. But a lot of the manufacturing happens here in the city, whereas most of the carbon fibre parts, so the metallic parts, are manufactured in the city. So the carbon fibre, and there's a lot of carbon on these cars, I'll talk about that a little bit later, is basically made at Bandura, or if the chassis are getting too big for our autoclave, they're subcontracted out to mates in Boeing or Ford Performance Racing who have larger autoclaves to bake the tubs. Testing occurs at Bandura. One issue that we have with our petrol cars is they're noisy, so all of the neighbours around Bandura complain, but they don't even know pretty much that the electric car is being tested, so that's obviously a big advantage of that. And most people think it's a race. It's not really a race. There's 8 separate events, and we have got 2 types of competition. It started, as I mentioned, in America, and it started in Australia a few years after the start in America. It started in about 1979 in Australia, and then we were doing internal combustion cars. You can see one of those down in the bottom right. But you can also use diesel, and you can also use ethanol. So we run 2 teams, the ethanol one, which is based up in Bandura, and the electric one, which is based in Sept, and Sept stands for the School of Electrical and Computing Engineering, as opposed to SAMI, which is the School of Aerospace Manufacturing, Mechanical and Manufacturing Engineering, which is where I'm based. So people say, well, what is Formula SAE? And you can describe it in a number of points, but these are some of the more quotable quotes over the years. It is the largest student engineering competition in the world. There's over 200 universities from many different countries now. There's competitions in many different countries. And as you probably read there's a whole range of different things. But the thing that I sort of really focused on is the last 2 points. It is the most motivating thing I've ever seen in my career in universities, both here and overseas. And it is one of the main things that the students learn is what I call the non-reversible nature of time and money. And if you asked yourself, I'm sure you've all done electric projects, how many, you're experienced engineers, how many of your projects have actually come in on time and on cost? Probably not that many. So the students are really forced into the real world of engineering by doing some of these very much hands-on things. I mean, the other way to describe Formula SAE is to basically describe the competition. So as you see, there's 8 separate events there. Won't run through all of them, but for example, the presentation event, students have exactly 10 minutes to sell their design for mass production to, if you like, venture capitalists, and that's marked by people in the industry, marketing people from Ford and Holden and some of the other car companies. The design politically that we've got facing this world, we can't keep doing, obviously, what we're doing now. I'm preaching to the converted, I realise here, but not always is that true for a racing audience. Or again, key issues. One of the things that I say in terms of countering perhaps the coal lobby and the politicians are, well, think of why people say the things they do. Think of the motive of it. I say this to my children and some of our students. Basically, scientists generally are looking for some underlying truth. They don't have a vested interest. Oops. They don't have a vested interest in things, so they're not after your votes. They may not be after your money. So if you actually look at the people that don't have vested interests, or maybe have an interest in the science, interestingly, this is something that's put together by the largest insurance group in the world, and it's taken a lot of the climate models, and they're interested in purely knowing what the real risk is, so that when they develop their insurance models, they've got the most valid models. So they put away the vested interests of things initially, and they've looked at a range of different models using natural forcing, so in other words, without human intervention, and then with anthropogenic forcing. And these are models that they've got, and the black lines on those models, I think, no, I haven't got one from Australia, but we can see the one from Australia down there. The black lines are the actual data, and the red lines are the models with human forcing, and the blue lines are if humans weren't here putting CO2 on the planet. So I think most intelligent people are now quite convinced that there's a real issue. Max Mosley, one of the key people in Formula One, wasn't talking about our Formula SAE cars at that time, but perhaps he could be. But he was talking about was the enormous technology that goes into Formula One cars. And it's interesting to see where that was presented. So arguably in the most prestigious journal in the world, in Nature, 2007, he came up with this, and he also came up with the fact that we really have to bend the Formula One technology to be more useful, because it wasn't really useful for where road cars were going or should be going. So Formula One is an interesting game, and Formula SAE is like a little bit of a microcosm of that, but without the experience and the dollars. So we first of all thought about, when we came up with the idea of electric cars, that what we should do is to reuse the energy. So KERS, kinetic energy recovery systems, seem to make a lot of sense. And everything comes down to the drive cycle. So the hardest drive cycle of all is going around a Formula One race, and this is the speed profile against time for Kimi Räikkönen's one of the fastest laps in the Albert Park Grand Prix in 2007. You can see it coloured by speed around the Albert Park track. So if you look at the deceleration levels here, so we're going from here 300 kilometers an hour to less than 100 kilometers an hour in 1 or 2 seconds. That is a massive amount of energy that normally just gets dumped in brakes, carbon brakes in Formula One. So we thought, well, obviously what we're doing, because we're looking at racing, electric racing, we should put kinetic energy recovery systems on our car. And very early on, we started to look at that. We were part sponsored by Holden with supercapacitors and so forth. But it gets just incredibly complicated to do that. And although there is most to be gained for this most arduous of driving cycles, we still haven't really got kinetic energy recovery. If you think too about during these braking events, so going down at this massive negative G, if you like, all of the weight transfer gets shifted to the front of the car. You can see that with the motorbike doing the stoppie, for example. So you really need generators on the front wheels, and there's not much point in having anything on the back wheels, because there's not actually an awful lot of reverse power going through there when you're under very heavy braking. So it makes for a very complicated racing car, and it makes for a heavy and more expensive racing car. So most people in Formula SAE Electric do not go for kinetic energy recovery systems. It's not because we don't think it's a good idea, it's just massively complicated. And one only has to see the challenge that Formula One has had to try and make systems work to realise that it's going to be very difficult and challenging for a small student team. It's an academic institution, so I thought we'd spend a couple of hours doing a bit of theory there. So, but then I thought, no, we probably shouldn't do that. What we will do is just give you a little bit more background in terms of the realities of trying to build an electric car. So, sustainable racing using power not from our brown coal infused grid, but using our conservation and renewable energy park, which is up in Bandura, is something that we've done. So we effectively use not always, not recently, but we've used entirely solar power to go racing. So arguably truly sustainable racing, at least in the power that we're consuming as we're going around the circuit. The first car, keeping it simple, was a retrofit of one of our early single-engined IC-powered with the Yamaha 450 engine. So we basically changed the back. We strengthened up the tub to put hard points in so we could mount some of the lithium batteries on both sides. And it was a very, very simple car. It used a brushed motor, a very simple controller, no differential, so normally you would have that on a racing car. But despite being a relatively simple car, it enabled us to get to the racetrack on time and be ready on time, which it wouldn't have done if we'd done anything complicated and taken on board some of the suggestions that some of the people were coming up with, you know, multiple hub motors and all those things. We'd probably still be building it now. But in 2008, it was, I think, the world's first all-electric Formula SAE vehicle, and it lapped the track as fast as most IC cars. So that was a very pleasing start. Won't go into this in any great detail, but when you're designing a race car, you really want to know the effects of different design parameters on really a track time, or sometimes the number of points you're going to get from those 8 events in Formula SAE. So Jeff Pearson, with a bit of help from me, came up with a points simulator, a little bit different from a lap simulator, but it enabled us to play games. So, for example, if we wanted to reduce the frontal area of the car, we could plug in something here, and we would see the bottom line would be how many points we would gain or reduce by the fact that we had less air resistance, a very small effect in that instance. But one of the other things it enabled us to do is if we look at the mass of the car, so the mass of the car, this particular model was 265 kilos, students had typically spent a huge amount of time and effort trying to reduce the weight of the car by maybe a kilo or 2 or 3 or 4. And you find that for every few kilos you lose, you only gain potentially 1 point, but you make the car more fragile, possibly less reliable, and so forth. So we use these kind of relatively advanced design tools to try to come up with rational decisions on how the car should be designed. So it is, if you like, a reality check. So the lap simulator is used to try to figure out how we can tweak our designs, how we can tweak our effort to maximize the number of points. Maybe not winning any event outright, but gathering as many points as we can out of that 1,000 total. And as you probably read there, the top 10 are spread across a relatively large margin. So out of 1,000 points, quite often, the top 10 cars, they're not within a point or two of each other, they're maybe within a few hundred points. And usually that means because they haven't got to the competition well sorted, and they've broken down, or they've had unreliability and problems associated with that. So all sorts of things. That's a very, very common issue. So the bottom line is you need to finish the car and the event preparation earlier. And every year we try to encourage the students to start early. And it's a bit like my standard joke when we do work for the automotive industry. The automotive industry is really very forgiving. If you've got an idea or a new product you'll put on their car, or you suggest to them, they're very happy if you can do it in negative time, with negative mass at negative cost, no problem. It's a very cutthroat industry. So we're having a launch of the new car. This isn't the new car, and I think Michael's going to talk about the old car perhaps a little bit and the new car in a few minutes. So I think if you're interested and want to come along to see the new car unveiled, there's the details. So it's in the design hub. That's building 100. This is building 80. So if you go up Swanston Street that direction, you get to a very strange looking building with lots of glass discs on. RMIT's most expensive building, apparently. It's designed by architects, so it doesn't function too well, but you know, it looks nice. No, I shouldn't say that. So if you're interested, how do they do that? Email? Okay. Michael will send that out. So I'm going to shut up now. I've probably talked for too long, and hand you over to the real players in all this, the students. And we advertise to the students the fact that why should they take all this extra work on? Well, they'll learn an awful lot more so than conventional degrees, and probably, usually, employers really appreciate all of the great advanced learning that they've done. So over to these guys.
So I'm Michael, and I'm the team manager of the RMIT Electric Racing, and this is Boban. Yeah.
Can I kick off with a question from last year's car?
Sure.
It in the
Competition
event,
yep.
where you do your lap as fast as you can. You cranked it up and got a really good lap time, and then it failed. What actually failed?
Well, our car didn't fail last year.
You didn't finish the event.
No, we did. Swinburne didn't finish. Swinburne, last year we won the electric competition.
Yeah.
And we had in the endurance event, there's 2 heats. So on the first one we finished, and we were the only, in the first heat actually, there was only about 6 cars out of 24, including combustion, that finished, and we were one of them. And then on the second one, in between the 2 events, we didn't get enough charging time, really. And so basically we just ran out of juice on the second last lap, was it?
Yeah, about that. Yeah. 2 3 laps.
So you can take your best endurance event. So yeah.
So this year we have 2 sets of batteries, so we don't have to. Yeah.
They're expensive.
So we didn't actually have a failure so much as we just.
You resolved the issue already.
Yeah, but we'll go through that a bit. I'll just go through. I won't talk too much about the competition because Simon's already done that, but more go on about. Maybe I'll just go straight to photos. A bit of a history of our car's evolution. Just like I'm guessing a lot of the cars that you are all a part of building, we sort of started from taking the combustion car from the existing RMIT Racing and converting it to electric. And that conversion has taken different steps. So the first car here, the green machine as we call it, basically started with all components off the old car, and we just slapped a big electric motor in the side and some batteries that we get a hold of as cheap as possible and that sort of thing. And it was, as a proof of concept, like Simon said, it did extremely well. And it was the first Formula SAE fully electric car, of which there is now multiple international competitions. So yeah, it was really just a lot of the parts we weren't thinking about weight at all. It was just about doing a quick conversion, proof of concept, see that it could be a real thing. And you can see here, it's not too glamorous, but it did the job. And then over 2009 and 10, the competition developed, and in 2010 was the first electric division of the same competition, which Swinburne and RMIT both entered. And you can see, again, we had converted a combustion chassis, but then more and more parts were changed to be custom designed for an electric purpose. And you can see the original red color, but then when we raced, it was the silver one here, the Sherman, which was the heaviest car we've ever produced. I think it came in at about 340 kilos or something like that, which I think was similar to Swinburne's weight last year, actually. But yeah, as you can see, more and more of the car was designed for the purpose of being electric, as opposed to just modifying an old car. Some of these photos are in a peculiar order, but that's all right. In 2011, we took it further again. With more involvement from the electrical engineering school, more programming went into it, and so more customized electronic control boards were designed, and we started playing more with the idea of trying to do, I think this is the first year we did 2 independent rear motors, which you can sort of see here, and which are still an evolution of which the ones here today are an evolution of. So independent chain drives, so 2 motors in the back, and we attempted to play with ideas like torque vectoring and yeah, essentially independent motor control, independent wheel speeds. Became a lot more complex than we had anticipated, so it never successfully worked to its potential, really, and it's still an area that we're working on today. So a lot of the developments of, yeah. And you can start to see that this car starts to appear more and more like the one we have today. 2012 was the same, further developments. 2012, we started to put together a bigger team and a better understanding of the challenges for an EV. But the shape and form stayed the same. We just evolved more in the electronics than in the mechanical side. Last year was a complete revolution for us, which is the car that's here in front of you today. We started the year with 7 students and finished with over 70. We designed far more than we ever had before, and it was by far our most successful car. being the first to be electric, we'd always been pretty successful, competing with Swinburne for first place in the electric, but we'd never really been able to show the combustion cars that we were competitive. And last year we won the electric competition by quite a large margin, but then also managed to beat our friends here at RMIT. We beat our own combustion team, and we came 10th overall, beating 14 other combustion teams. And we're starting to see the electric competition grow. So last year was 3 cars, this year is 4, and next year there'll be 7 cars. So out of, I think there's 28 teams registered in Australasia, we're seeing that percentage grow more and more electric, and we're seeing more and more people come to us to express interest in converting their SAE teams to be electric. The basics of the vehicle, of this vehicle, I guess, was 2 independent motors with direct chain drive, and Bob on here is the chief electrical engineer, so he's probably better to answer questions about how the electronics work. But the success of this car and the success of building the team has put us this year into our most ambitious project yet. We are building a car from the ground up. Nothing from this car is going onto the new car, and we are building from the ground up for the purposes of an EV. So as opposed to making mechanical or making existing car things work for us, we are designing for our own purposes from the ground up, which is also proving to be an exceptionally large challenge, as I'm sure a lot of you have experience in. And we are switching a couple of our key components. So we're going back to a single motor, which, yeah, do you want to talk more about the new car?
Yeah. Do we have any photos?
Yeah, some parts coming back.
Okay, so this year we've moved to a single motor and a differential. The main reasoning behind that was we could build a lighter car, and given not much progress was made towards torque vectoring, there were dynamic gains to be made from running a differential compared to what we had previously, and it's been more focused on building a well-suited car and having a car completely designed to be electric rather than getting parts of the combustion team. We've got a more powerful car than last year. There were several issues with the motor controllers we're using. We've got 2 new sets of batteries that we're assembling that you can see in the image over here. So there's significant design changes in the battery packs. They're going to be a lot safer this year. We've moved to a space frame. This is the motor we're using. So MRAX 228, it's made in Slovenia. It weighs about 12 kilos and can reach 100 kilowatts peak. This is the drive here that we're using. It's made by Unitech in Germany. It's really hard to know what sort of interest you guys have in specific parts or what you want to know about the car. So if you've got any questions. Yep.
Using any sort of limited slip differential or just a straight turn?
Yeah. We're using, so part of the decision to switch back to a single motor was we could buy a limited slip differential, and that would, for us, just eliminate a key part. And so we do have it's a Drexler LSD, which is basically off the shelf, and that's a variable that's just known. So we eliminated all of the programming for this year to give us more time. We are looking to set up a 2-year development of future cars and look down at the parts, so that gives us 2 years to know exactly what the rear of our car is doing and know exactly what the diff is doing.
Yeah. Any other questions? Yes.
Yeah. Yes, the motor, is it the polyphase motor, 3-phase, 4-phase, what?
3-phase.
3-phase motor. And air-cooled?
Water-cooled. Given the drive is also water-cooled, we believe we could get a better density overall, and also you need to be really careful when reading data sheets about under what conditions you can reach those ratings in air-cooled motor. For example, this one's been designed for gliders, so to reach the rated power ratings you need 70 km/h winds going over the motor, which are unrealistic given the position in the car.
Is Slovenia a hotspot for motor development and technology, or how did Slovenia come up? It's quite a small little pokey Slavic country.
Not particularly, but it's driven by an individual who started this company originally just to make electric gliders for his own personal use. But it's a quite amazing product, and I think Siemens tried to buy him out at some stage, and he's had the motor independently tested by Siemens, and it is up there with the best.
Can you elaborate on the design specifics of the motor itself?
Yep, so it's a permanent magnet synchronous machine, and it produces axial flux, so you have higher torque, lower speed. So gearing is a lot easier in terms of being able to use a chain drive rather than moving to a planetary gearbox if you had a higher speed motor. Free phase, we've chosen one for resolver output. You can have different sort of position measurement devices attached to it before you purchase it.
What voltage? Because I know they come in various voltages.
Yep, so we got the high voltage one, which is 450 volts RMS.
How many poles?
I believe it was 10 pole pairs from memory.
Do you want to describe a little bit about the battery and the control system that you?
Yep.
Yes.
So the control system for the car is developed in-house. It's needed to be developed in-house because of a lot of specific rules requirements that we have to follow. In particular, certain safety features have to be implemented using analog circuits, and also developing that knowledge allows carryover from year to year. We've also been developing our own battery management system this year. That's the first time we've developed our own in-house battery management system. Previous years we've bought off-the-shelf items, but they've never been adequate given most car manufacturers develop their own anyway. So there's very few out there, and they're not targeted after large companies, and it's just anyone who's really desperate or can't afford the time or money to make one themselves.
We also had a lot of trouble with them in the past, and with the cost and know-how, and it seemed like we do have a lot of knowledge obviously here in the electrical engineering and school, so it gave us the opportunity to make one of our students, a final year student, is doing his final project on it, and even that has turned out to be a mammoth task.
So it's been quite difficult to develop a reliable BMS, because my experience in e-bikes and e-bike batteries is the BMS is the first place you look when you have a battery failure. It seems to me to be quite a notoriously unreliable part of the electric motor concept.
Yeah, we've had pretty simple ones in the past, and that we never really got what we needed out of them, and that was part of the reason why we decided to do our own. Also because of the nature of the rules specific to us and the context of the vehicle, we found that we couldn't find ones off the shelf that were necessarily.
Given that you're only racing, you're only going to charge the batteries 2 or 3 times on the weekend, and you balance the batteries before it's put on the car, the BMS is not really doing anything except meeting the requirement of the rules.
Well, actually, we want to try to get as much testing done beforehand, and we want to look after these batteries, considering there's such a large capital investment. So we're looking at keeping these for at least 2 years, maybe more, and we want to cycle them as many times and test the car as much as possible before the competition.
But you can test the batteries individually after each time you use it.
But it becomes a very, we're running 120 cells in the new car, and that becomes a very labor-intensive and very challenging problem, especially when we have a lot of, part of the hardest nature of this project is the transitional nature of students and the unreliability of students.
Just from reading, I've read other articles where they say that they've lost their batteries due to the failure of the BMS, and the shunt kicks in, flattens the battery absolutely completely, and so they have to throw the battery away, not because the battery was bad, but because the BMS brought failed.
I'd say poor handling for, well, you're probably best to talk about
Yeah. Well, it can't really discharge the batteries too quickly. You don't really need a BMS that's that aggressive. Also, you need to keep in mind, because our vehicle is so small, our power density of the cells is greater than most electric vehicles. So the heat produced by our batteries is a lot greater than you would have in other vehicles. So we also need to monitor the temperature.
I think what's happened
compared to
because of the shunt is kicked in, the battery's got that. Someone really needs to run battery and whole cell and whole thinking you don't necessarily notice which the others will charge up and shunts will kick in and you don't necessarily notice them installed until it's too late.
Well, you have more control over those sort of issues by developing in-house.
As far as the batteries go, what chemistry and construction are you using the batteries?
We're using lithium polymer cells manufactured by Kokum. The team's quite familiar with these branded cells. They've worked quite well in the past, and they're not overly volatile. They're quite safe to the point that they're used in Boeing planes. When they had battery problems when they brought out their planes a few years ago, they switched to Kokum to increase the reliability of their aircraft.
Kokum is they're the Swedish group, aren't they? They also Kokums, is that right?
No, it was originally Dow Kokum, so they were owned by a large multinational chemical company. Then they split off, and now they're just called Kokum. Or they're also branded by another name in the States. It slipped me, but they also manufacture the batteries for Formula E.
They're Korean?
Yeah, they're Korean.
So the using LiPo, so that's the construction. What chemistry?
I can't tell you off the top of my head.
You don't know if it's a lithium iron phosphate or if it's NMC or.
Is it lithium cobalt?
No, sorry, I can't recall.
So in the battery management system, and it's not something I'm that familiar with, but you scan every cell, or you scan groups of cells, and what criteria does your management look at? Is it thermal quality or over voltage, under voltage, current through the cell?
Oh, we look at all of those parameters you've listed.
For every cell, not groups.
Yeah, we have series cells, so every single cell is measured. We don't have any in parallel.
The BMS is a big issue. And just maybe to amplify the point regarding, yes, it's a relatively short race, so you do 20 kilometres in each endurance team, which is kind of nice because it means you haven't got to have that many batteries. It's ideally suited to an electric race, whereas a Formula 1 race is you've got to carry a huge amount of energy if you're going to do it there. The issue is that the fact you've actually got to do a lot of sorting and practice. So the batteries, the batteries going to get used a very short time in the race, but the batteries going to be used a long time in the shakedown. And you've also got to have 4 or 5 drivers in the car. And these are sometimes novice drivers, so you've actually got to train the drivers as well. If you're going to do well in a race, obviously you've got to try and make sure that your weakest link isn't too weak. Sometimes that might be the driver. So there's driver training that comes into it as well. So 4 or sometimes 5 drivers are all going to have a fair amount of time in that car under pseudo race conditions. So there is quite a lot of work going through the batteries, not just the 220 odd kilometre hits and the acceleration event.
So having said that, I guess there's something to say, keeping the car fairly simple.
Oh yeah.
And getting effective runtime, it's totally more complicated, potentially more powerful, but not testifying. Single
biggest mistake that novice student and the novice engineers make is they completely underestimate how long things will take to do. And although it's amusing to see just-in-time technology and driver training on the race, it's also quite dangerous too. So in some, it's almost the norm for most teams to actually turn up on the race day or on the second day of the race with a completely unsorted car and completely unsorted drivers because the non-reversible nature of time has come back to bite them. So that's the biggest lesson that these guys learn.
Victoria University by the time friends moved there, they couldn't get on the track.
Yeah, we've been there and done that. You know, we've got there early on. We got there on the Sunday of the competition, which started on the Thursday beforehand, with a really untested car. So you can never have too much testing. It's something too that will come back to bite the students, and these are immovable deadlines.
Don't worry about that though. FBR did the same thing too. When they started, I was there when they did that. They went to the GP, they hadn't tested the car, so you're not alone in that.
It's not that unusual. And I mean, if I could go off and pretend for a second, and the petrol car, where we kept it very simple things. The non-reversible nature of time, plus the enthusiasm and motivation of the students. Before we went to Detroit, 2 students broke the record of how many hours continuous they worked without sleep. Have you got any idea what it might be?
100?
No, they got two students. Yeah, 59. Yeah, 59 is the record, and they don't do that on my assignments.
Speaking of one of the acceleration tests last year, they had a what do you call it? Automated start feature. What do you call it?
Launch traction control.
And the first year they designed that, it didn't work properly. So they continued over the second year.
Yeah.
And they actually won that component of the event.
Yeah.
They spent 2 years on that and had a lot of testing for a whole year on it.
Yeah. I mean, there's a question on how you should actually manage and think about the whole project. Should you effectively try and build the car every 2 years and try and win every 2 years, or should you, as we do, build 2 cars every year, which is probably a bit extreme.
I guess it's
team involved this year for next year.
Well, I used to have discussions with Harry Watson. Some of you know he was the head of mechanical engineering at Melbourne University, and his philosophy was that you start each year with a clean sheet of paper and a clean new group of students, and that maximises the learning. I said, yeah, but it'll guarantee you'll never ever win a race.
Or maybe even learn more in run.
Yeah, I'll probably not get to a race.
And do you really learn a lot if you can't run?
Yeah, that's right. I mean, they've been very ambitious, Melbourne University. We nearly always beat Melbourne University.
They actually changed that philosophy last year and came third. So.
Yeah. So one of the things that they did a long time ago was to build their engine from scratch, their IC engine. Never do that. You don't realise how much development work has gone into typically a Japanese or European or whatever engine. Just don't touch anything on the engine. Don't try and reinvent the wheel, because there's hundreds of years of optimization going through that.
One actually on the shelf.
Yeah, we all do that. We all do.
Do you know you're racing this year?
Calder.
Calder is.
Yeah.
Still the same weekend? Or?
Yeah. It's 11th to the 14th of December.
Just got another question on the batteries. What's the S&P of the batteries? So how many series and how many parallel?
112 in series, none in parallel.
Wow. And what's the amp hour capacity of pouches?
The typical 16, maximum 17, so they're the manufacturing tolerances given to us.
And how big are the pouches?
They're about 150 mil by maybe 100 mil. So they weigh 400 grams maximum.
Let me show you. Show you battery containers up there somewhere else.
These are the containers here, and that holds 28 cells. What's there?
What C ratings are they doing?
It was 8C continuous, maybe. I don't quite recall. Haven't had to deal with the batteries recently.
You mentioned that this year the plan is to run 2 separate battery packs for each part of the Enduro. Did you have to go into how that means you manufacture the battery packs in terms of being able to actually get them in and out in a reasonable amount of time? What considerations did you have to make to that?
Yeah, it was a key design feature mechanically from the start that our chassis had to allow for the accumulators and batteries to be removable, because maintenance and servicing of them, they became one of our biggest failure points last year, and one of the biggest challenges. Obviously, they cost us the second endurance heat, and they Swinburne between events, between days, had to take their car back to Swinburne, whereas we could just take the batteries out and leave everything else. So Yeah, it was from the very beginning, our chassis, and like I said, the new car is designed from the ground up to be for an EV. The chassis is designed to accommodate accumulators, and we had to make some mechanical changes fundamentally to how we design the car based on that.
So is that, is there any modularity within each of the packs that you are putting in? Or once you've taken the pack out, is it then still a sealed device that takes a long time to disassemble and reassemble?
It still takes a while, but they are modular within that as well. So the car has, this car has obviously one in each side pod. The new car has 4 accumulators that all sit behind the driver's seat to lower COG and everything to do with that. And then within that, on the design, it's segmented into batches of 5 cells, I think. Yeah.
10.
10 cells.
Yeah, it's sort of hard to see here, but there's
So 10.
these
Oh yeah.
bottom-
So those you can see 3 sets there.
So 10, 10, and 8. There's intermediate dividers that aren't in this image.
So yeah, we have rules around fireproofing and insulating between certain energy capacities. And so the modularity of it allows us to do that, and also allows us to service them a lot easier without taking apart the whole thing. But it is still, they're going together this week after the new ones, but it is still going to be a very fiddly process, as it always is.
So that's a new regulation from SAE about that separation of.
It's been that every year they change it and it gets harsher and harsher, and next year we'll have to redesign the whole thing again because they've changed the rules again. But most of the rules have existed since the first competition, and just incrementally, especially as more teams come on board in Germany, there's more actual interest from people in the EV industry who help shape the rules.
So there's still a huge amount of the EV rules are still derived from the German ones then? I know in the early days it was almost exactly the German rules with very few modifications.
If I got to that, and because we're pioneering and built, I think, the world's first all-electric car, there were teams from around the world that came and saw that. And the SAE traditionally was learning itself, because the SAE is an IC, effectively an IC institution. So we were a bit involved in trying to draft the rules, but I mean, I'm not an electrical engineer, so we got some electrical engineers from Holden to help draft the rules, and so the rules were very good. In the first year, we really didn't know ourselves. Obviously, safety is extremely important, because there's more than enough to kill several students in this thing, and we want to make sure that it's totally safe. So safety is number one, and there's over 100 pages of rules. So some of the design decisions may not seem that optimum, but when you know the background behind it, the fact that there's an enormity of rules very much configured around the safety for the students, then it sort of makes a bit more sense.
The rules are now global as well, so there are local amendments, but the fundamental rules, probably 95% of them are global. And there was actually, at the recent Formula Student Germany, there were quite a lot of EV fires. So that's why they've redesigned the rules quite substantially around accumulator packaging for next year.
I guess it's part of the pioneering you're doing, help developing the technical standards required.
Yeah. I mean, it's a learning exercise for everyone, including myself.
And the best teams in Germany, I think Delft and TU and a couple of others, they're pioneering EV technology within the university, and Delft start of this year broke the speed record for an EV over 100-meter sprint, I think it was. That's like 75 minutes.
Fastest 0 to 100.
Fastest 0 to 100
In what speed?
2.9.
2.9.
2.9 seconds.
From 0 to 100.
Yes.
In 2.9 seconds.
And they're getting so worried about the accelerations of these cars, they're actually trying to limit it by considering not allowing hub-mounted motors in each wheel.
Wow.
We're still a bit behind that, but we're starting to get back to the setting ourselves up.
Formula E? Do you time with that as much? Or?
No, not really.
But we watched the race with interest, and I think one of our electrical team members was noting that we're running pretty much the same EV battery and accumulator technology as they are. Pretty much quite similar, same cells almost. And, yeah. But it is. They're also, you can see from the way they've designed their competition that obviously they gave everyone their car this year, but they've done some things to their rules which perhaps are slowing the rate of EV development. like the fact that they change drivers, perhaps. I've talked with a few people who think perhaps if they had made them forced to switch batteries halfway, that would have forced the evolution of that sort of technology.
I was thinking that probably been better off having like the Australia, the touring cars and having 2 shorter races.
Yeah.
Rather than switching the cars.
Yeah. But it'll be more interesting as it develops, because next year when they start to open up the teams to develop their own technology.
So after the Grand Prix, how quiet was this year anyway? The probably was down anyway. I could barely hear it.
But EV technology is being pushed a lot by F1 itself as well. So the amount of recovery they're getting in curves is obviously phenomenal.
I think the big difference is next year when they can build battery packs.
Yeah, absolutely.
All right.
Very good.
I've got to run away.
Any more questions? I know some of us have got to go off.
I've got to take my sister to the airport.
Michael's got to dash to the airport. So thank you, Michael. Thanks, Robin, and thank you all for coming. Feel free to have a look at the car. Yeah, that's what I said.
They got school holidays at the moment.
That doesn't exist. That doesn't exist.
No, that's what me.
No, they don't. No, they do. Yeah, the school holidays and the university holidays in Australia or in Victoria are completely out of kilter.
Okay, just thank you to everyone in Google Hangouts and on YouTube for watching this, and a very informative discussion from the RMIT crew. For those that want to stay in touch with all things EV, go to the ATA Melbourne EV Group Facebook page. I'm not supposed to call it Face Crack, it's Facebook page, and become a member, join us, and let's grow the EV movement together. So goodbye to everyone out there in interweb land, and we're all going to drool over the car. Well, actually, just before we go, maybe we should just turn the camera around to show the if that's at all possible for our techie. Adrian, the amazing tech, and here we have it. This is the old car, out with the old, in with the new. Driver here, motor back there, goes that way very quickly. So that's enough technical stuff from me. So we'll see you next month. Okay, bye-bye.
Bye.